Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number... Seemingly every field, every science, branch of mathematics, whatever you're interested in, there's time series data there. And there's no shortage of methods to do something interesting with it, like outlier detection or forecasting. So wouldn't it be great if there was one tool that could bring together different fields and different methods all in one common framework for doing time series analysis and exploring a variety of methods on several different data sets? Today on the show, I speak with Ben Fulcher about the Comp Engine project. It's a tool you can learn more about at comp-engine.org. In fact, grab a CSV or an Excel file that surely you have around and drag and drop it and see what you get. While you're testing that out, Ben and I will talk about this project, what it does, and how they built it.
My name's Ben Fulcher. I'm a senior lecturer in the School of Physics at the University of Sydney. So we do a fair range of things in my group. We like to think about neural systems and the mechanisms underlying brain dynamics and brain structure. And we also have a strong focus on understanding the structure of time series and dynamical systems, complex dynamical systems in general.
And what does the Venn diagram of those two topics look like?
A fair bit of overlap, because obviously a lot of the questions you might want to ask about the brain is how it changes over time, how it processes information. All these things are distributed, time-varying processes. So a lot of people are getting much more interested in using modern complex systems and particularly time series analysis techniques to understand the kind of dynamical structure and mechanisms underlying information processing in the brain. So there is a fair bit of overlap.
Well, we should chat again sometime, maybe in the future, about the neurophysics and complex systems side of it. But in our series on time series, I wanted to invite you on, especially to talk about the Comp Engine. For listeners who aren't familiar with it, could you talk a little bit about what this project is at a high level?
Yeah, the Comp Engine specifically is one arm of the type of work we do on time series analysis. And this was a website that we made to allow users to share and compare their time series data. So as part of my PhD, I collected over 30,000 different pieces of time series data, kind of recognizing that time series analysis is a very interdisciplinary field. People measure and study the dynamics of systems in biomedicine, in astrophysics, theoretically, in applied math, and in engineering. It's hard to find a field where they don't care about time series or the dynamics of what's happening in the system that they're interested in studying. And so we decided to try and bring together all of this diversity. Typically, it's kind of studied only in the little local area in which people work. So economics people like to study their economic time series. Biomedical people like to study their biomedical time series. We kind of thought, are the methods that these different people use all completely different? Is there something to be learned from combining them? Are the data that they studied, are there kind of hidden connections between, seemingly diverse systems from across science and industry? And so we decided to make this platform and a range of tools actually around this idea of trying to bring scientists together around both the methods that they use and the data that they measure.
As you were mentioning, every field, well, not every field, but it certainly is the case that some fields have developed their own specialized techniques, or at least it seems that way on the surface. When you get some familiarity with them, it might not be surprising to find out that some of these techniques are kind of two sides to the same coin, perhaps, or, I don't know, maybe people are developing these radically new abstract ways of looking at things. What's the level of diversity in all the methodologies and techniques you explored?
Yeah, this is kind of a question that cuts to the heart of the whole project, I guess. When we were looking at the literature and we were coming a little bit from the outside, both being trained in physics when we started this project, we kind of saw a lot of papers coming out where someone would say, here's a new method, look how well it does on this data set. And then a week later, someone else would say, here's a new method, look how well it does on this data set. And they were coming often in the same field, but often, as I mentioned, across all these different fields. And it always leaves the question open when you see a paper like that. How well would another method have done on that problem? Or did they just pick a data set in which their method works well? And of course, every method is going to have its strengths and weaknesses on different types of data. And so we wanted to understand that subtlety. There's no best method for every problem. You need to kind of tailor your methods to your problems. And so we wanted to understand how these different methods relate to each other. And we found a lot of redundancy when we put all these scientific methods together, and we came up with a way of implementing and coding algorithms for over 7,000 different methods for capturing a different type of structure in a time series. When we put them all together, we found a large amount of redundancy. So a method one person might use in one field might have a different name to someone in the next building on the university using a different method, but actually what they're doing is relatively similar. So there are a lot of examples that we outlined on both kind of surprising connections and kind of surprising differences within a field as well.
What's the infrastructure like that look like? It seems like implementing that many methodologies would require a cleverly structured code base, maybe a bunch of things interacting. What are the mechanisms under the hood of Comp Engine?
So Comp Engine is the website for comparing data. So maybe I talk about the data side. So that's where you can drag on your own time series data at comp-engine.org. And you can drag your time series on, and it will interactively show you a bunch of time series from around science. So of the database of over 30,000 time series, and you can contribute your own, so it's growing every day. It will find the connections between the most similar types of data in other fields, and you can explore it interactively, see what properties make your data similar to other scientists' data. There's that comp engine side, and then there's the kind of highly comparative time series analysis side, where we're more asking about the methods that scientists have developed to analyze structure in time series. So these are things like stationarity, the properties of my time series changing over time, different autocorrelation properties and things from information theory, saying how predictable is my time series, what's the entropy of my time series, different model fits and other types of network, converting a time series to a network and finding the properties of that. There are 7,000 different types of methods that you can use to turn a time series into a kind of interpretable summary statistic of the types of the properties and the patterns in that time series that can be quantified as a single real number. And so that's a kind of separate enterprise of comparing the methods. And there we have a bunch of different software tools that it's not so complicated. Once you boil it down to that way of thinking about it, you just take a time series and turn it into a single real number. Then every one of these different scientific methods can be turned into a little algorithm that has as input a time series and output a real number. So the challenge is really just in the infrastructure is just putting all these different methods together. And once they're all together, you've got a big package of all these different types of time series analysis methods all in one place. And then you can start to do really cool science, and often for applications as well, because now you have access to thousands of different time series analysis methods, whereas in the past, when you're working as a single scientist, probably subjectively you can only cover a handful of things. Now you can kind of have access to this very broad library of analysis methods.
So I get a couple of benefits. If I start from my univariate time series data and I put it through here, it winds up in this, goes through your feature engineering process and winds up in now a common standard that's sort of invariant to the source of the data, which is really interesting. What are some of the novel ways people might then compare across seemingly unrelated time series?
In terms of this kind of comparing across different types of data, so this is the comp engine data side of things, where you might have your piece of time series and you're just curious, right? I know that there are other people studying time series in very different disciplines. So maybe I'm from astrophysics and I study a particular type of star, and I'm just curious what other types of scientists are studying similar types of data. So I can drag my data onto this Comp Engine website, and it will pull up both model-generated and real-world data. So you may find that actually, someone in applied maths has been spending the last decade studying time series or ODE type of model that actually looks very similar to the data that you're studying from the star, your favorite type of star that you study the dynamics of. Or maybe you find someone in chemistry who's studying ion channels who has very similar types of patterns in their data. And so it can, or even someone statistical, there's also simulations of statistical models in the database. And if you find a connection between your data and a particular class of statistical or stochastic models, it kind of suggests that maybe that area of theory is relevant to understanding the mechanisms in your data. So you have two ways of kind of finding interesting connections. You can find other scientists who are studying systems that have surprising commonalities in terms of the structure of their data, and maybe you want to talk to them and say, what methods are you using? What questions are you interested in asking? And also when you find a match between real data and a model, you might then go, maybe I should talk to that, the statistician or the mathematician who studies that model, because it looks like the structures in their data is very similar to the structures in the data that I like to study.
Yeah, it seems like there's a really good opportunity there for serendipitous discovery. Like maybe, I know I study algae blooms, and unbeknownst to me, that somehow correlates heavily with sunspot activity that an astronomer has put in, and I might not have otherwise figured that out, and perhaps there's a real mechanism there. But at the same time, I don't know, maybe all of the kind of known things scientists have already figured out, and there aren't any, easy mysteries or low-hanging fruit. Do you have any feedback from users about the kind of serendipitous discoveries like that, or any novel stories of people finding something they otherwise might not have known?
Yeah, I mean, when we originally put all these data into one space and tried to find connections between different types of data, the most compelling ones were when we had model-generated data clustering in a similar space to real-world data. And that often captured model mechanisms that had actually been used in that type of area of science. So we found stochastic models that are similar to those used in finance clustering around all the financial data. And we found models that had been used for heartbeat analysis clustering with all the heartbeat data. So this kind of all made sense, but just the fact that they all kind of sit there in the same space kind of suggests a kind of automated way of seeing the connections between the theoreticians, and that's another aspect of this, the theoreticians that study dynamics of their models may be looking for real-world systems in which they could apply their models to. So yeah, we found some interesting connections like that. And if there isn't a good connection, you can put your contact details when you upload your data into CompEngine, and maybe in the future someone uploads a piece of data that's very similar to yours. And I guess one of the core parts of this enterprise is finding the types of data for which we don't have good models. So actually when there's no neighbor, and you've uploaded a piece of data that has structure that we've maybe never seen before, and we haven't come up with a good model for that data yet. That kind of is a way that we can also stimulate, what are the best areas for our theoreticians and our statisticians to develop models for that question. If you want to make progress in a field, you don't want to study the things that we're already good at. You want to focus your attention on the types of structure in the real world that we don't yet have a good explanation for.
Is there, in that regard, is there some intent to kind of crowdsource time series problems? That if I'm a scientist in some arbitrary domain, I should publish my data, and perhaps I'll benefit from the insights of many researchers working in these just more mathematical layers of the techniques?
Yeah, for sure. And I mean, I guess that's another benefit of having this big database, is to avoid the type of cherry picking that can happen in the methodological literature. So the fact that we now have an open database that people can contribute to, so we call it a kind of living library, where it will get bigger over time as more and more scientists contribute their data to it. We can then benchmark and assess our methods for time series analysis on very large and interdisciplinary set of data. So when you have a new method for, say, forecasting, and you want to go, well, what types of time series data does my forecasting method work well on? Rather than kind of handpicking a few classic examples, you can download this full set of time series data and say, well, it works really well on rainfall, but it doesn't work so well on space data, but it works really well on, this kind of really periodic data from this field. And so you can kind of get a really broad sense of across science, where does the strengths and weaknesses of a given method. And if you don't have this kind of unbiased collection of time series like this, researchers are left to having to manually pick data sets, and that process is never as systematic as it could be with access to this kind of broad interdisciplinary library.
Thanks to this week's sponsor, Quantum Metric. To all the digital leaders out there, how would it feel not only to know what your customer is experiencing, but how many others are experiencing this too? I think it's about time we put our customers at the center of our decisions and get ahead with real-time insights, way before a code freeze. It might be beach weather outside, but for retailers, the holiday season has already begun. 2021 holiday e-commerce sales are expected to exceed 2020 benchmarks. Are you prepared to capture every customer revenue opportunity? With Quantum Metric, you can be. Their unique approach to the digital customer experience helps today's top retailers and e-commerce brands quickly identify and prioritize the big and small revenue opportunities that keep customers engaged and coming back. Stay off the naughty list this upcoming holiday season by reducing customer friction, increasing conversions, and personalizing the shopping experience. Want a sneak peek? Visit us at quantummetric.com/pod offer and see if you qualify to receive the 12 Days of Insights offer using the code SKEPTIC, all caps. This offer gives you 12-day access to their platform coupled with a bespoke insights report that will help you identify where customers are struggling or engaging in your digital product. Some restrictions apply. If you're doing anything related to e-commerce, you've got to have a look at Quantum Metric and see if it suits your needs. Head over to quantummetric.com/podoffer. And while you're there, use the code SKEPTIC, all caps. With regard to this being a living library, do you have any concerns about growing pains, where there'll be stages at which the scale becomes difficult to manage?
Yeah, we haven't gotten there yet, but you can imagine some data sets now being massive. So when someone wants to dump a huge database into the library, we do have the ability to restrict the number of time series that are there. We really want it to be a kind of diverse reflection of the type of data in lots of different fields, rather than every time series that's ever been collected, which would go beyond the scope of what we're able to do. But, if there's enough of the type of data in heart rate analysis, and there's enough of the type of data that people study in economics and, astronomy and etc., we kind of really just want to be as broad about the types of fields that we're covering rather than completely comprehensive.
In that regard, is the data in some way, obviously you have some sort of curation process, which would be interesting to hear about, but also from like a category, are you kind of saying yes or no to some data sets, or is it come one, come all?
We haven't said no yet. The library is still mostly what I've developed by hand. But yeah, for now, it's come one, come all. So feel free to contribute your data.
And are there any specific areas that you think you're especially looking for, or where there's been a lot of interest, perhaps? Whether it's, weather data or biological time series. Guess what's been a real hot topic on the engine so far?
The engine itself is quite new. Most of our work has been on the method side. So yeah, the comp engine itself, it was just recently launched last year. And so it's still kind of starting to grow. And it's more that kind of interesting, I've got a piece of data, I wonder what its things are like it. But where we really think the scientific utility is what that database allows for scientific methods. And so the focus of our research has been more on comparing methods for time series analysis, with comp engine being a kind of more playful accompaniment to that, which we think also enables, as I said, different ways of doing cool science now that you have access to a big library of data.
In regard to it being playful, I would certainly echo that and encourage listeners to check it out. We'll give the URL again at the end, but do you want to share it now in case anyone's at their machine?
Yes, comp-engine.org, and that's for anyone to just play around with their time series data.
Yeah, and you can bring your own and upload, or you guys have kind of a catalog of pretty diverse options. Could you speak a little bit to some of the things people will find in there?
The history of this engine comes all the way back to me starting my PhD, when the scope was tell me everything there is to know about time series, and I barely knew what a time series was. And so the engine kind of reflects that process of me as a student trying to learn and read lots of different types of literature on what types of people are interested in time series. And so every time I found a type of person or a type of field that works with time series data, I'd try to find as much data as I could from that field and add it to my library. And after, 10 years, so that was started in 2008, after over 10 years, that kind of became more formally put as this comp engine library of time series data. And so you'll find me when I was looking through all the different stochastic models and simulating data from stochastic models, from ODE models, from lots of statistical models, all of those types of interesting models that physicists and mathematicians and statisticians play with when they think of dynamics, whether you're studying dynamical systems or whether you're studying physical systems like pendulum or coupled pendula, or whether you're studying ARIMA models in statistics or economics. So all those types of processes are in there. And then there's lots of real data as well. So lots of open physiological databases and all sorts of different meteorological data, rainfall, lots of audio, animal sounds. And so whenever I could find a kind of open database, I kind of tried to add it to this collection.
Yeah, the animal sounds were kind of a surprise to me when I first got there. And I was like, oh yeah, in fact, audio is a time series. And you can do some pretty neat things with it, like find similar sounds in the system using presumably the same techniques as I would use to find similar, weather patterns or stock ticker data.
Yeah, that's right. The underlying mechanism for finding matches between time series is the Catch-22 feature set that we developed. So this is when we took those 7,000 different features for time series analysis, all these different methods that I mentioned before, and reduced them down to 22 canonical properties that we think are a good representation of diverse data. And so it computes those properties and tries to find time series with similar properties. And that tends to work pretty well, whether you're looking for similar types of audio or similar types of stock price time series. Yes, that's what's happening under the hood, is that Catch-22 feature set, which is also an open thing that people can play with and use for their own data.
Yeah, could you tell us a little bit about that dimensionality reduction process? What takes place as you go from thousands of values in a vector down to the Catch-22 vector?
This was a big step in our development of this tool. So, like I mentioned, I'd spent some years collecting thousands of different time series analysis methods that turn a time series to a single real number, and I ended up with over 7,000 of these numbers from different areas of time series analysis. And then that takes a long time to compute for a single time series. A lot of those are redundant, so they're highly correlated, like I mentioned before. And so when you have a new time series and you just want to get a good idea of the different types of structure in that time series, you probably don't want to spend all that time computing all these thousands of things. So we wanted to kind of reduce the redundancy and both keep as much information in this feature-based representation of a time series as possible. And so what we did was we took those 7,000, took those that were the most robust across different types of data, and then applied them to about 100 different classification problems. And so we took the time series features that performed the best on those different problems and then clustered them to reduce the redundancy, and we ended up with 22 natural clusters, and we took a representative from each of them, coded it into C, and then have wrappers now for R and Python and Julia. So that was the other issue, that the original feature set was coded in MATLAB, which not everyone has access to. And so we kind of reduced it down to, we think, the most important 22 numbers that you could measure from a time series, at least our best current guess, and made that as available as possible.
Well, given the diversity of time series data, that's kind of a high-order achievement. Do you have any insights, or could you, share some of what those features are, and if you have any thoughts on how they all made the grade?
I mean, they tend to actually capture the types of categories that a lot of people would think of when they're thinking of what types of time series analysis methods have been developed to date to summarize the structure in time series patterns. And so I mentioned before, there's things like the distribution of values. So does a time series have a bunch of outliers, or is it approximately normally distributed, or does it have a particular skew? There are properties like that that tell you just about the distribution of values in your time series, so nothing to do about their time ordering. There's a bunch of properties that kind of capture linear dynamics. So a lot of people, especially from physics or in neurophysiology, would go from their time series and almost jump straight into a Fourier power spectrum of the data. So what types of oscillations and frequencies of oscillations tend to dominate the variance across the time series data? So there's a bunch of features that do linear correlation properties, or in statistics, you might think of the autocorrelation function, which is closely related to the power spectrum there. So there are a bunch of these types of properties. There's also some properties from entropy. So how predictable is the time series? My average surprise of computing the next value in the time series given patterns that I've seen before. So this kind of class of complexity measures that come from information theory and engineering. And then there's also some features, some more interesting and harder to categorize features, including things like what physicists like to study, which is kind of fractal scaling properties in a time series, using a method called detrended fluctuation analysis. And stationarity, there's some measures on stationarity. So how do the properties of the time series change through time? So if I looked at the first half versus the second half, would my properties be very different? And you can capture that in different types of statistics. So yeah, those 22 canonical features do tend to cover the range of kind of expected areas that have been covered in the time series analysis literature, which is developed over decades in many different fields, as I mentioned.
Thanks to this week's sponsor, Seamless ML. Based in Cambridge in the United Kingdoms, Seamless ML is a fast-growing company that has doubled revenue every 18 months since inception. They're currently hiring data scientists and quantitative researchers. If you're interested in using machine learning to do algorithmic trading, this might be the team for you. Let's talk about the culture. Seamless is not about plodding along and doing good. It's about working like hell to achieve a standard that is extraordinarily high, and then getting the satisfaction that comes with that sort of super achievement. An exceptional team, a great culture, and the opportunity to apply machine learning on algorithmic trading is a great opportunity for you to explore your machine learning chops in practice. If you believe you could be a good contributor to this team, head over to seamlessml.com/jobs. That's seamless, SEAMLESS, ML.com/jobs. So a big part of this project is being able to benchmark all those different methodologies against a diverse data set. Can you tell me a little bit about how you benchmark it? Is it just predicting the next value or an average of the next 10? What's a good metric for deciding how to evaluate these techniques?
Yeah, so again, this gets to the core of some of the issues that we were trying to address here, because typically every scientist has their own problem or type of problem that they're interested in. So some people are really interested in forecasting, some people are really interested in anomaly detection, right? So they have a large database of time series and they want to find unusual time series. Many people in biomedicine are interested in classification. So what's different about my time series when I'm measuring it from someone with schizophrenia versus someone who's a healthy control, or I want to detect Parkinson's disease from an audio recording, so what features should I measure from a piece of audio that might predict if someone has Parkinson's disease or is healthy or is at risk of Parkinson's disease. So everyone around science, when we looked, was kind of having their own type of problem that they were interested in. And each of these problems requires a different approach, even with the same class of problem, like anomaly detection. If you're trying to find anomalies in one class of time series, the best features or methods for doing that will be very different to if you're trying to find anomalies in a different type of time series data. So this is kind of why we wanted to bring all those methods together and give them all a chance to shine, because there is no one best method for everything. The key in being a good scientist and a good data analyst is picking the methods that suit the problem at hand. And so rather than a focus on publishing a method and go, look how well it does on this one thing, we wanted to move towards a world in which when you publish a method, you go, here's my new method, here's how it relates to other types of methods, and here are its strengths and weaknesses across all these different problems that it could be applied to, rather than just focusing on a small hand-picked subset of problems and methods. We wanted to allow researchers to both compare across thousands of different methods and compare the performance across thousands of different types of problems. And so with Catch-22, we took the first step in this direction. We just took 93 different classification problems for time series analysis, which is very easy to benchmark. You just get a number of how accurate your method was on that class of problems. But in future, and currently, we have students broadening this out to a much broader range of types of problems. And we want to, in future, have a way where you can drag your algorithm onto our server, and it will say, oh, here's a new algorithm. It's doing this better than anything that's ever been done. Or you might drag your algorithm on and goes, oh, nice try, but someone's already come up with a very similar algorithm in the 60s, and maybe you just weren't aware of it because you haven't read this paper from decades ago in a different literature or whatever. So we want to kind of open up both our data and our space of how algorithms are benchmarked and proposed.
Well, with all these efforts, it seems like you've really lowered the bar for doing a lot of these comparisons and looking at a broad spectrum of data. With that in mind, do you have any concerns about opening up the opportunity for doing too many comparisons and finding some spurious correlation?
So now when you're a researcher and you want to say, I want to classify this type of time series versus this, typically what you would do, so a concrete example, maybe we go with that Parkinson's example. You're a mobile phone company, you're spying on your customers, but you're a good-hearted telecommunications CEO, right? You want to send them a text message when they're at risk of developing Parkinson's disease so they can go and get help early, right? And so if you could detect that early, then just automatically listening in on your customers, you might be able to help your population get treatment early. So you want to say, well, what features should I be measuring from the audio that would get me a good prediction of the types of people that are likely to develop Parkinson's disease and that I should recommend go and get some sort of checkup? And so typically when you have a problem like that, and that occurs all the way over science and industry, anomaly detection from credit cards or sensors on a production line, you want to automatically detect if there's a problem on your production line. What should you measure from that time series? At the moment, there's kind of subjective process. So a scientist might go, oh, it looks like this class of time series has a bit more periodicity. Maybe I try and measure something about how periodic the time series is, or looks like that's got big outliers. Maybe I should measure something about the outliers. So there's that subjective process. And when you then go and produce your algorithm based on that feature, you never really know if that was the best thing you could have measured or not, because you haven't compared it to the other types of methods that you could have used from across science. So from our tools that make available thousands of different methods at once, the scientist now has the ability to compare across all of these different methods and automatically pick the types of methods from across science that work well on their data. And they can then go and explore that literature, try and understand those methods, and develop an algorithm based on that class of ways of thinking about their data that work the best. And you're right to flag that, that process, even though researchers would have had access to that breadth subjectively before, now we're kind of making it upfront that you're explicitly comparing these thousands of different things. And so you can be statistically open about that comparison. In particular, you can be rigorous about controlling for those number of comparisons to quantify your probability that you've picked up something spurious in terms of controlling your false positive rate under that. It tends to work really well. The signals that people want to measure, normally they do have the power to compare across thousands of different things.
Well, when appealing to scientists as users, you're going to get a collection of people with very diverse technical backgrounds, some very sophisticated with a lot of good programming chops, but some, I guess at a minimum, know how to work Excel a little bit with their data, and everybody's got time series. What's the barrier to entry to seeing if your solution is going to be productive for a researcher?
Yeah, so I guess this is why we've tried to make these tools that make it very easy. So you do kind of need a little bit of a coding background. I mean, if you're going to try and tackle a classification or regression or anomaly detection problem, I guess you do need to have some coding background, whether you're doing it in industry or whether you're doing it in science. We haven't made an Excel version yet, but I think if you're fitting models and doing high-level statistics, even basic statistics, you should be familiar with at least one of the coding languages. But yeah, Comp Engine was one way that we tried to get people at least into this way of thinking, where you can really just do it with clicking, dragging, and a graphical interface, at least so you can get a flavor for the types of methods. And we are developing some similar online interfaces where you can drag your data set on, and it will do the feature calculation in the background and tell you the types of features that are working well for simple classification problems involving time series. So we're currently developing with some students some tools where even if you don't have a coding background, you can at least drag your data set on and it will give you some insight as to how well you can classify different labeled groups of time series.
That'll be a good extension to the existing drag and drop I've been playing with on the site today, exploring just some junk data and then comparing it to some of the data sets that are there. With that in mind, do you have any other exciting things you're comfortable talking about that are coming down the road? What's the future of the tool?
Yeah, so similar to some of the directions that you've mentioned there in terms of how can we really benchmark all these different time series analysis algorithms and really explicitly drive towards progress in the field, because this practice of coming up with a new algorithm, not comparing it on data and not comparing it against good benchmarks of what already exists in the literature is commonplace, and it's very hard to get over because the process of comparing to thousands of different things is time consuming and difficult to do manually. And so we're really focusing now on tools that can help people when they propose a new algorithm to put it in the scientific context and the interdisciplinary context of what's already been proposed, so that we can be even-handed about the strengths and weaknesses of what scientists over decades have already developed. And like I said before, identify the types of areas that we're not very good at yet and that we need new methods for. And so hopefully all these scientists and people in industry who are trying to develop new methods can focus their attention on the areas in which we really need to focus. And for scientists who already have their favorite methods that they use day to day, can try and understand how those methods fit in to alternatives that they could be using and what the strengths and weaknesses of their methods are. So when they come across a new problem, they don't take the biases of their old experience with them. So just acknowledging that different types of problems and different data types require different types of methods to be good at. Whereas we often see people go, oh, this method was best when I did it last year, so I think it'll be best on this new data set. When you have this culture of comparison, you can kind of start to see which methods work well on which types of data, and when they do badly, we need different approaches for those problems. So we're developing new tools to kind of automatically benchmark analysis methods, and we hope then that the real progress that gets developed. So whether someone in astrophysics develops a new method we drag it on and we say no one's done this before and it's outperforming everything on this wide range of difficult problems, that we can really quickly accelerate that progress across all the other fields of science so that these real developments, when we find them, don't just get trapped in one discipline, but actually someone working on a production line or someone working as a data scientist in some industry or finance company can go, oh, actually there's been progress in astrophysics. I want access to that method as quickly as possible. And so we want to develop tools that kind of accelerate this sharing of knowledge across the sciences, especially because given that we're all working on the same fundamental data type, which is a time series, and yet we don't really talk to each other as much as we could.
Absolutely. Yeah, it's an existing issue, and I'm glad to see there's some work going in the right direction on it. Ben, can you remind listeners where can they go online to try this tool out themselves?
The Comp Engine tool, they can go to comp-engine.org.
And where online should they go to follow you and your lab?
Yeah, and to find me, you can follow me on Twitter at Ben Fulcher, BenFulcher, and there's also an account for where I tweet about time series, which is Comp Time Series, also on Twitter. And there you can find links to all these feature-based approaches for highly comparative time series as well.
Excellent. Well, I'll have links to all those in the show notes. Ben, thanks again for taking the time to come on and share your work.
Carl, thanks for having me.
That concludes another installment of Data Skeptic Time Series. Thanks to our sponsors this week, Quantum Metric and Seamless ML. Our guest today was Ben Fulcher, myself, Claudia Armbruster, associate producer, Vanessa Bly does guest coordination, and our host, Kyle Polich.